Statistical methods work well when they're used in the situation for which they've been designed. But care must be taken when using the methods in order to make sure that they're used appropriately so that sensible conclusions can be made. In this video, we'll look at a few situations in which care must be taken when using the method of linear regression. Let's begin with an example. Chlorofluorocarbons, or CFCs for short, are chemicals that were widely used in refrigerants and aerosol cans. But they are known to contribute to ozone depletion in the upper atmosphere. Concentrations of CFCs in the atmosphere have been measured in a variety of locations around the globe since 1977. This plot shows the concentrations from 1977 until 1990, measured at the top of a dormant volcano in Hawaii. From the plot, we can see that there is a strong linear pattern in the growth of CFCs over time. And using the method of least squares, we can find the equation of a line to describe that growth. Doing that, we get that our fitted value of CFC from the regression line is about negative 19,000 plus 9.71 times the year. The slope is approximately 9.7. So we can interpret that as, on average, the concentration of CFCs is growing by about 9.7 parts per trillion each year. Recall that the intercept is the estimated value of the CFC concentration when time is equal to 0. Of course, in the year 0, CFCs hadn't yet been invented. And the negative intercept here is meaningless, as you might expect anyway, since a negative concentration doesn't have any meaning. Interpreting the intercept in a practical way only ever makes sense when having 0 as the predictor variable is in the range of our data. We can also use regression lines to make predictions. Suppose we wanted to predict the CFC concentration in 1995, say. So we could plug 1995 into our fitted equation and then predict that the concentration in 1995 would be about 309 parts per trillion. However, we might not be willing to trust this prediction because 1995 is 5 years outside the range of our data. And in fact, in 1987, a number of countries signed the Montreal Protocol, which laid out a schedule for phasing out the manufacturing of CFCs. If we extend our data beyond 1990, we can then see the effect of the Montreal Protocol. The atmospheric concentrations of CFCs begin to decrease. So using our fitted regression line to make a prediction for the CFC concentration at 1995 wasn't a good idea. We were making a prediction beyond the range of our data. Doing that, making a prediction beyond the range of the data, is called extrapolation, and extrapolation is always dangerous. We may think that a linear model is a reasonable way to describe what we see in the data, but that doesn't mean the pattern of a linear relationship exists outside the range of the observed data. Now let's take yet another look at our fitted line for the data before the Montreal Protocol. For the range of data illustrated here, it seems that the straight line model fits well, but look a little more closely. The points are tightly scattered about the line, but they seem to follow a pattern where there are points above the line and then below the line and then above the line. A systematic pattern like this is an indication that another, more complicated model might fit the data better than the straight line. But this was a pretty subtle pattern. How can we make sure we don't miss a pattern like this? We can use residual plots. Residual plots are useful tools because they can exaggerate these kinds of patterns, so then we're less likely to miss them. Here's a plot of the residuals versus the year. Recall that a residual is the vertical distance from a point to the regression line. Some of the residuals will be negative, corresponding to points below the line, and some will be positive. In this residual plot, we can see the systematic pattern of mostly positive residuals, then negative residuals, then positive residuals. corresponding to points above, then below, then above the line. If a line is an appropriate model for our data, the residual plot should just look like random scatter about 0, which is not the case here. We see the systematic pattern. Sometimes, instead of being plotted against the predictor variable, residuals are plotted against the corresponding predicted values of the response variable. For regression with one predictor variable, as we're doing, this has the effect of simply changing the scale on the horizontal axis, using the regression line to get the new values. But we interpret the plot in the same way. That is, random scatter implies an appropriate model was fit to the data, and a systematic pattern, like we had in the CFC's example, means there must be a better model. Here's one of my favorite examples. Here are 4 data sets, each with 11 points. These aren't real data, but were created by a statistician to illustrate a point. Note that for each of these data sets, the summary statistics, including the means of x and y and their standard deviations and the correlation between x and y, are all the same. As a result, the estimated regression line would be the same in all 4 cases. So, could we conclude that the relationship between x and y is the same in all 4 data sets? Let's take a look. Here are scatter plots of the 4 sets of data, and here are the corresponding regression lines, which are the same in each of the 4 plots. We can see that a linear model is only appropriate for the first set of data. The second set would be better described by a curve. In the third plot, it looks like we have a nice linear relationship, but the regression line is shifted because of one stray point. And in the fourth plot, if it wasn't for that single outlying point, there would be no linear relationship. The statistician's point in creating these data sets was to emphasize that the numbers are not the whole story. Always make sure you plot the data first to see if a linear model is a sensible choice. These 2 data sets from the previous 4 show examples of influential points. Both of these examples have a single point that, if we removed it from the data, the resulting regression line would change by a substantial amount. Here is another example of an unusual point. In the relationship between average crawling age of babies and temperature, we see that there is one point that is far away from the regression line. Looking at the plot of the residuals, we see that the magnitude of its corresponding residual is much larger than the magnitudes of all of the other residuals. In the distribution of residuals, this is an outlier. But is it an influential point? We can remove the point from the dataset and refit the regression line to the remaining points to see if the line changes by much. The orange line is our new regression line without that unusual point, and the black line is our original regression line with all the data. We see that the slope is very similar and the intercept is shifted up just by a small amount. So although this point doesn't fit the data well, it's not an influential point. Points that are influential are often outliers in the horizontal direction. Outliers in the horizontal direction are called leverage points. Sometimes a leverage point falls into the pattern of the rest of the points, and then it is not influential, as the line would be the same with or without it. Sometimes a leverage point can completely determine whether or not there appears to even be a linear relationship. In this sketch, there does not appear to be a relationship between x and y, but if we have one more point up in the top right, we get a regression line that shows a relationship. So this leverage point is influential. In this situation, we wouldn't want to conclude that there is a linear relationship between the variables when it is only due to one single point. Here's a summary of the cautions from this video. While regression is commonly used, it can also be easily abused. Careful consideration must be given to the range of the data and not to extrapolate beyond it. Always start with a scatter plot of the data and follow up with the plot of the residuals. Consider whether a straight line is an appropriate model for the data, and watch for influential points.